Hey, what's up, physics? Um, what we're going to do is do a quick review on what fluids are, what kind of things fluids can exert in terms of like force and pressure and things like that. We will then look at some of the measurables for when fluids are not moving. So that's going to be our goal today. We'll start with what the heck a fluid is. A fluid is a state of matter that can flow. So we're looking at liquids and solids. So being able to flow, going from one point to another. You can have gases that are fluids. Since gases do flow, we don't think of it this way, but wind is an example of a gas flowing from one point to another. The most convenient way we looked at measuring fluids was with pressure. And, typically with the types of pressure that we measure things in, like our tires or inflating a basketball, we would use pounds per square inch. But, in the wonderful world of physics, measuring force over area, we don't use pounds, we don't use square inches. What's more commonly used is the Pascal. And a Pascal is when force is found in newtons and the area is in meters squared. So we did a little activity a couple weeks ago where we looked at finding the pressure that we exert on the floor and kind of looked at how that pressure changed based on the area of our foot pressing on the floor. So today what we're going to do is we're going to look at two different types of ideas here. The first idea is called Pascal's principle. Pascal's principle is going to be what we use to describe how hydraulic lifts work. So sounds very physics-like. So Pascal's principle, I'll give you the definition, then I'll translate it for you, is that any change in pressure applied at any point in a confined fluid is transmitted undiminished throughout the fluid. That is fancy talk. That is straight up physics jargon there. Okay. So the translated version of this is what happens when you squeeze a tube of toothpaste. So if you put the lid on toothpaste and you start squeezing the fluid inside, what happens is that pressure that you exert inside that tube is transferred throughout the tube. And if you squeeze hard enough, what will happen is the pressure will be too great for the tube of toothpaste and you'll have a blowout, and somewhere it will explode. That's kind of the idea behind Pascal's principle. So what we're going to do is we're going to apply Pascal's principle to the concept of how a hydraulic lift works. Hydraulic lift. I'm not sure if any of you guys have heard just the term hydraulic. Typically, hydraulic systems are systems where you have fluids that do work on an object. So a hydraulic lift is something that can lift something very, very heavy for us. And it can do so by applying and changing the pressure of the fluid inside. So we're going to look at how hydraulic lift works. We will have two equations today to put on your note card, or just keep in mind. If you don't have your note card with you, maybe time to start a new one. That's going to be our goal. So what the heck is a hydraulic lift? A hydraulic lift is a force multiplier. A force multiplier. So very similar to when we looked at simple machines and how a lot of the simple machines were things that allowed us to use a small force to get a big force out of it. A hydraulic lift is very similar. It's a force multiplier that uses this idea, a closed system where there's a fluid and you can apply a small force on something and get a large force out of it on something else. Okay. And the reason why this happens is because of Pascal's principle, the pressure stays constant. So for us, what we're going to look at is our first equation. And I'm going to write this equation on the board here so you guys can see this. Just need to do a little of this. I'm going to make that larger for you here. Okay, so our hydraulic lift equation that we're going to use, sometimes you'll see it like this. force 1 over area 1 equals force 2 over area 2. Okay, and usually the idea is one of these sides is going to have a smaller force and area, and one of these sides is going to have a big force and area. That's kind of the idea behind a hydraulic lift. So that first equation, this equation right here, is going to be what you are going to write down. I'll kind of draw a makeshift hydraulic lift so you guys can see what the heck is happening and how these things work. So make sure you guys get that down. All right, so the idea behind a hydraulic lift is this. Usually, okay, I'm going to draw this. This is going to be just awesome. Great sketch, great artwork. Okay, so usually a hydraulic lift uses these things called pistons. So piston is what our piston is going to look like here today. All right, I'm just going to color that in here. All right, so we have this really little piston over here. We're going to push down with a force. All right, we just call this force 1. And what we get is a really big force over here on that one. Okay, now the way that this works is because inside of here, there's this hydraulic fluid. Okay, so there's this liquid and it is filled to the brim. And so just think of this as like squeezing a tube of toothpaste. I push down, and what happens is the liquid is transmitted throughout. Because this has a small area, we can apply a small force, and we can get on this large area, because this piston is much, much bigger, a much bigger force. So it's how they multiply forces with that. So typically what you'll see on the problems is you will see sorry, don't need to look at me anymore, right? What you will see is usually a small force coupled with a small piston and combined with a big force combined with a big piston. Okay, so that's step 1. All right, step 1, using Pascal's principle as a force multiplier for hydraulic lifts. So you need to get that down in your life. The second thing we're going to look at is swimming under pressure and what happens when we are submerged in a fluid, whether that fluid be a gas or a liquid. So we're going to use this example here. Most of you in your lifetime have swam down to the bottom of a pool. So if you swim down to the bottom of a pool, depending on the depth of the pool, in my hometown, our old school pool, the old school diving boards had a depth of 13 feet. Now, when you swim down, you will notice that the pressure at that low depth, okay, in this example, 12 feet, I probably used the old Sydney pool as an example. You'll notice that the depth is, or the pressure at that lower depth is much greater than it is at like 2 feet. And this whole concept by which, scuba divers and how scuba diving works, and try to have a video for you guys down the road on how that all works. But what we need to understand is that as we go deeper in the fluid, the water in this case is going to apply more force at 12 feet than it is at 2 feet. So that's why it feels like somebody's standing on your chest, and why it's very, very difficult, very uncomfortable. You feel your ears pop and all that stuff. In a fluid like gas, when we are hanging out in our atmosphere, you'll notice that you climb up a ladder 10 feet, you don't notice this big change in pressure. We have to go ascend or descend a couple thousand feet before we even notice this change in pressure, before our ears pop. So this is going to be your second equation here. Second equation is going to be calculating the pressure in a fluid. So the pressure is equal to this little thing that looks like a P. It's a Greek letter that stands for density, times H. H stands for the depth that you have been submerged, and G stands for good old gravity. So the measurements that we need to have these things in, that little, the little lowercase looking P thing, needs to be a density in kilograms per meter cubed, the depth needs to be in meters, and the gravity always for us is going to be meters per second squared. So basically, to find the pressure, you're going to need to know three things. What's the density of the liquid that you're in? How deep are you in the liquid? And what is the gravitational force on that planet, which we usually use as 9.8. So we'll just do a very easy example with water, because a lot of times we use water as our main liquid here. Okay, so the first thing you need to understand about water is that water is measured with a density of 1,000 kilograms per meter cubed. Okay, 1,000 kilograms per meter cubed. So if I descend in a pool or anything like that, and I go down like 3 meters, which is a little more than 9 feet. So we go something like this. We have 1,000 times 3 meters. Don't worry about sig figs right now, times 9.80. This would be the number of pascals that your body would be experiencing. So we are looking at, like I said, don't worry about sig figs right now, 29,400 pascals. Or, if you don't like that, 29.4 kPa. So, pretty beefy. That's the second equation we're going to use, and we're going to use that to describe pressure as we swim in different things. I mean, this could be water, this could be oil, this could be mercury. You can imagine that mercury would probably apply a pretty big pressure to us. This could be air, if we knew the density of the air in that given area. So that's going to be what we look at for this little section here. Okay, so we're going to try to keep it simple and do a few problems. Now, format of these problems will follow as, or we'll go as follows. We will have a space on your classwork in Google Classroom where you will do these problems. You'll show your work, try to pay attention to sig figs using the equations that I just gave you. Pay attention to what labels are in, because that's how they make a very easy question into a little bit more difficult question by changing some of the labels for you. So these are the 4 problems. You guys can just handwrite them out, take a picture, upload it in the classroom. If you have questions, send me an email at my Raider Mail, and we'll kind of go from there. All right. Okay. Well, good luck. I'll see you around.